Okay, everybody, welcome back to class. This technically makes our last class section for the entire year. The last section is going to be assembly and application of particular materials, primarily as applied to the great domes of the world. We're going to be looking at the Cathedral of Florence, the Renaissance Dome by Brunelleschi, St. Peter's in Rome, and of course, St. Paul's in London. This is a great chart showing the size and the height of all the great domes of the world. You know, we've seen the Pantheon many times in ancient Rome. We can see the Cathedral of Florence, the height of St. Peter's, St. Paul's. This is a great chart to have to compare the height of things in other buildings. Okay, so we're going to be really talking about three different ones: the Cathedral of Florence, St. Peter's, and of course, St. Paul's. This next slide is really what the world of architecture looked like when they were building things without a lot of steel cranes and scaffolding. So we're looking at wooden scaffolding as kind of a formwork, a temporary formwork for each one of the constructions. Before we get to the domes, I'm just going to show you, these are, of course, some of the wooden timbers in the Gothic cathedrals. So we're looking at, as you know, Gothic cathedrals weren't building domes, they were building naves with tall spires, but we're looking at is an incredible layer of timber frames to design the actual nave and of course the structure. What I was showing you earlier is that this is actually a temporary formwork, the wood formwork, and then the stone and masonry is applied on top of that. This is a drawing from David Macaulay's book, Manual of Construction. I think you've seen a lot of his cartoons and drawings. We can see that, of course, the stonemasons are hanging up there on scaffolding. Of course, the wood formwork is just simply temporary. So let's kind of take a look at in depth the Cathedral of Florence. There's a YouTube video if we have time in a lecture, I'll kind of show that to you. But really, we're looking at the early formations of the Renaissance, 1436. It's made of masonry, surprisingly all clay tile faced with stone and marble. There's a wonderful book called Brunelleschi's Dome. And it's really the entire narrative is how this was actually built, how this was created. This book doesn't have a lot of visual diagrams and images, but it does tell the story beautifully about how this thing was actually built and constructed. If you're not familiar with this in history, is that the cathedral, in other words, the dome, this floor plan was actually open for about 50 years because nobody could properly figure out how to actually span that far and actually build a covering for the roof. So you would be having sermons and sanctuaries in an open, uncovered dome. Of course, they weren't sure how to figure out how to build the dome and of course the covering. So Brunelleschi won the competition to build and how to structure the dome and cover that incredibly large open nave. So we talk about the nature of domes. We're looking at really several different distinctions. I've talked about this earlier, the pendentives, the drum, the cupola, and of course the lantern at the top. So it's really interesting to see that this, you know, you'd be having mass and sermons in here with a cathedral that was completely open with no covering or wood roof or dome. So what happens was, you know, Brunelleschi was commissioned and won the competition to do this. Not only did he have to design the actual dome and have it constructed, he actually had to build all the machines and the parts to figure out how to actually build this thing up in the air like that. You know, of course, we didn't have large enough timbers to span across. So of course we had to go up as a large masonry dome. And these are some of Brunelleschi's machines he designed and created to actually build this. So it wasn't really just, he didn't just design the dome, he had to design the machines to actually physically build the dome itself. These are just incredible sort of early Leonardo da Vinci constructions on how to build these particular buildings and domes. It's really wonderful. These are very far advanced machines for, you know, the early Renaissance, 1450, 1495. We can see a mule-drawn machine being powered by the animals to turn. And of course, there's a complex imagery of machines, chains, and weights and belts to actually build these things. So here's a large section of the dome after it was finished. It's roughly about 180 feet across. It was actually the largest dome in the world at this time. A very, very compelling project to do for pretty much kind of a novice in architecture. We really didn't have formal training in architecture at this time. Here's a cutaway section showing the actual structure of the dome. Now, this is all a mixture of nothing but bricks and clay tile and mortar. Now, again, what I was saying is, after the Pantheon, we're not building with concrete masonry. I'm sorry, we were not building with concrete because, of course, the fall of the ancient Roman Empire, they destroyed the formula for concrete. So we're using masonry and stone, of course, definitely not steel. But we're looking at is Brunelleschi's creation about how to actually construct the dome. So we're looking at the structural ribs, the brick masonry, and we can see that the structural brick masonry are these skins in between each one of the shells. So we're looking at really two different shells. So the inner shell and of course the outer shell, both with brick masonry. Of course, it's faced with clay tile for the roofing material. Of course, the inside is faced with plaster. But part of the success is the brick masonry. This is not a very clear slide, but we're looking at is what he created was a herringbone pattern in the brick masonry inside the two shells. This actually creates a spiraling effect. If the bricks were laid horizontally, repetitively, that probably wouldn't have a much more of a kind of a bracing, because the herringbone pattern, when they turn the tiles vertically, is, of course, it creates the sort of helps the tension between the top of the dome and the bottom of course, the drum. Looking at it as a very clever way to do brick masonry to structurally span the opening of the vault, and the dome, and of course, for the structural capacity for the actual structure itself. So this image is showing you the herringbone pattern in the actual dome itself, and of course the pattern. The technical term, if I'm pronouncing this correctly, is called spina pisse pattern. We can see that actually there's an architecture teacher that rebuilt parts of this dome as an experiment to see how this actual building would have been constructed. But we can see that the herringbone pattern of these flat clay tiles embedded into the dome itself. Here's a cross section of the dome. What we're looking at is you can actually, as a tourist, you can actually walk in between the two shells. If you have an opportunity to actually stand in line for several hours, you can actually walk through the two shells and of course appear on the top of the cupola. It's a really wonderful sort of way to experience the dome. So we're looking at is, here's kind of a preliminary model of this architecture teacher that actually built an example of how the dome has been constructed. Is that, the bricks are not the contemporary bricks we see in brick veneer in our houses in North Dallas or North Texas. We're seeing the brick tiles that are laid as a structural companion that were laced to each other. So we're looking at is pretty much everything was built as a wooden scaffolding temporarily constructed. And then of course we see the workers actually building the actual structure. Now, of course, the tower is built with brick masonry, not steel or iron. Of course, it's faced with probably travertine stone or marble or limestone. But the scale of this, look at this, people are tiny. This is a huge dome. This is the largest dome in the entire world at the time of the Renaissance. So if you look at the cross section of this, you can clearly see the structural integrity that Brunelleschi designed as kind of a brilliant mathematician, structural engineer, and an architect. And so we can see that the layers of the structure is actually constructed on, because remember, in Gothic cathedrals, the structure was exposed in Gothic cathedrals. You would not see a concealed structure. So the Renaissance architects would consider Gothic architecture as vulgar because you're seeing the structure on the outside of the building. Flying buttresses were really supposed to be the structure. But of course, the Renaissance architecture was considered modern because the steel ribbing and of course the flying buttresses were concealed into the walls. So you would never see flying buttresses in a modern Renaissance cathedral or chapel, or building. So we're looking at is, of course, the roofing material, the clay tile with, of course, the marble on the exterior facade. Now, the marble was actually laid probably and finished in the 18th century. The marble was much added later after they finished the cathedral. But it's interesting, you can see parts of the cathedral are actually not quite finished on the outside. Here's a wonderful image of Brunelleschi's tower, the dome, Giotto's tower on the left, and of course, parts of the city of Florence. These are pictures of walking through the two shells. There's an incredible series of ramps, staircases, and of course, these little hidden corridors. They're really not meant to be visited by tourists, but of course, this is how the actual workers would construct the dome. You would actually be inside these two shells to actually build this incredible model. What was interesting, what I can't really show in this image is I don't have pictures. That's actually the workers. This is a very sort of daring, challenging structural construction to actually do this. What happened was, is either be this incredible layer of scaffolding inside, and also they would water down the wine to serve to the workers because to sort of cancel out or assuage their fear of heights, because of course the dome was so tall, it's very intimidating to be up there. They would actually cover the large, we see the line that says 180 feet, that would actually cover the base of the dome where it meets the spring line for the arch. Then of course I would cover that with canvas or wooden scaffolding so the workers wouldn't be able to see how far above the ground they actually were. So it was a mixture of watered down wine to alleviate their anxiety for heights. And of course, the entire shell would be covered with this incredible layer of wooden scaffolding to sort of disguise the height of this particular dome. Okay, so this is really revolutionary for Renaissance and what's considered modern architecture at the time. Again, I was saying that the marble is actually added much later in the 17th century. So you can see part of the unfinished cathedral, the dome, and of course, part of the finished, the marble that was added much later. Here's a wonderful image of course, the dome with Palazzo Vecchio and, excuse me, the foreground. So the next one we're going to look at is St. Peter's Basilica, the large dome, of course, Michelangelo's. This didn't quite rival the height of Brunelleschi's dome. Let's go back to the original chart that has all the domes together. We can see that St. Peter's dome was much taller and larger. It probably wasn't quite as large of a span because, of course, St. Peter's is 160 feet apart. The cathedral is 180 feet across. Of course, the height was surpassed by Michelangelo. What's interesting is that these architects, you know, they lived and breathed their entire architecture pedagogy, their life and work. Let's go back to Michelangelo's St. Peter's Dome. He was 71 years old when he got the commission to design the dome. Of course, he was assigned the floor plan as an original Greek cross plan. But of course, as the church kept getting larger, the sanctuary kept getting larger and bigger. And so, of course, the sanctuary kept getting larger. And the facade was actually finished by Moderno, not Michelangelo. So the original Great Cross plan was designed by Michelangelo, and then, of course, later finished by Moderno. I think Michelangelo died by the time this dome was actually finished. What we're looking at is, of course, again, two shells. The inner shell, which deals with the scale of the sanctuary in the nave, and of course, the outer shell is scaled for the height of course, the city of Rome. Now, what happened was, in particular in this sanctuary, is that when the sanctuary kept getting further enlarging and much larger than the dome, is that the view from Piazza San Pietro's was, the dome was getting obscured by, of course, the extended nave. So the travesty of this is that you really can't see the dome from Piazza San Pietro's. You can only see the dome from other parts of the city of Rome, of course, and you can see it from the back side, which actually is the Vatican Gardens. But this is a credible model that was built in wood and is featured in the Vatican Museum. And it's so large, you can actually stick your head and look inside the dome and see all the different layers. Here's the outside of it. What I was saying earlier in the Renaissance is that, you know, Michelangelo and of course Renaissance architects, you would not show buttresses because that was considered inappropriate and vulgar in architecture. So Michelangelo builds these columns to disguise the fact that he did need buttresses to counterweight the thrust of this enormous weight of the dome on top of the actual building. So normally in Brunelleschi's work, you don't see the buttresses at all because he's cleverly disguised them inside the shell of the structure. It's really remarkable that somebody can build this entire structure with mostly mortar and of course clay tile or bricks. In this example, Michelangelo was doing, of course, a brick dome, but it's faced with plaster and of course limestone or probably travertine marble. You can clearly see that the buttresses are disguised cleverly in these Corinthian capitals, these columns. Again, if you look at the cross section, there's two shells, the inner and the outer shell. Of course, you can actually navigate in between the two shells. Of course, the stairs are those little ribs that you see in the cross section. A pretty spectacular sort of experience to walk from the bottom of the church and go up and pop out into the top of the cupola. So this is actually part of a tourist attraction. What's really remarkable is the fact that Michelangelo separates the dome from the sanctuary with these little glass layers. So the glass windows actually are kind of a gap between the drum and the dome itself. So of course, these windows let incredible, powerful light conditions into the sanctuary. And this is a drawing of the cupola or the lantern on top. If you finish the climb from the ground floor to the very top, you actually get these incredible views of Rome from the actual lantern at the top. These are drawings of course, the plan, the lantern, and of course, the section. So this cross section is showing that actually to build these things, you would actually be using a wooden scaffolding. It's, you would have to be actually building a temporary wooden formwork. So this is what actually all the dome constructions would look like. You would see a wooden formwork, and then of course you would see the construction of the dome after that. So pretty much there is a temporary layer of nothing but wood scaffolding around the actual domes. So let's go back to the chart originally, because we're going to be talking about St. Paul's dome, which is actually 3 layers: the interior layer, the cast iron and brick layer, and of course the outside of the shell. Okay, so we're looking at St. Paul's Cathedral, even larger and probably taller than St. Peter's Dome. Sir Christopher Wren, he really actually rebuilt the entire city of London after the fire in 1663 or 1666, I think. So we're looking at a kind of the phase of architecture between Baroque and Neoclassical. Of course, Neoclassical, we're borrowing the styles from ancient Greece and Rome. So we were looking at a triple shell dome, a mixture of masonry wood, iron bars, and wood timber frames. Here's the outside of it. Again, we're really not supposed to be showing buttresses or flying buttresses, of course, an architecture that was considered vulgar. So we're looking at it as a very tall dome scale for the entire city of London, not just for the interior sanctuary of the church. So the dome is actually made of 3 shells, 3 materials. The inner shell, of course, so there's 2 shells. If you can see my cursor, the inside is a layer of brick. And of course, the large perpendicular dome at the diagonal is, of course, brick and probably cast iron. And of course, the outer shell, designed for the scale and the height of the city, is a mixture of wood timbers and, of course, cladding with iron. Here's a plan of the cathedral. You can see that in each one of these little quadrants, the thrust of the dome is so large that these enormous piers carry the weight of the dome back, and of course, down to the sanctuary floor. So here are some cross sections, really unique sort of section. There's actually 3 domes superimposed in each one of these. We can see the interior shell, which of course has the murals and the frescoes. Of course, the interior shell is actually the structure transferring the weight of this enormous cupola, or of course the lantern of the tower, then back down to the masonry walls of the actual cathedral. So here's a section and of course a plan. Here's a diagram of the section of the dome with the cathedral. You can see that, of course, the crypt is, of course, the foundation, the basement, where all these, look at this, the middle shell, the center one, shell number 2, of course, the iron and the brick and masonry shell continues all the way down from, and transfers the load from the piers all the way down to the ground. So it's interesting that the structural capacity is transferred from the top of the dome all the way down, of course, to these really heavy masonry walls. Of course, you can see that in, of course, the floor plan is that the walls are very heavy and thick because we're transferring the load of the dome, the lantern down on, of course, to the ground of the sanctuary. It's a pretty intriguing section of 3 different domes. You're probably thinking, well, why didn't Christopher Wren just actually make the interior of the nave the same height of the dome on the outside? Well, probably because the scale, the proportion of the sanctuary is due to the fact that if you were actually to build the interior of the dome with what actually went all the way out to the outer shell, is that you probably wouldn't see the actual space of the cathedral. So by having the scale of the interior dome proportioned for the scale of the actual church, there's different relationships here. Of course, the outer dome is scaled for the actual outside of the city of London. And of course, the structure, which is not visible, is actually proportioned or scaled for the actual cupola that transfers the load from the top, of course, down to the sanctuary. So here's a cross section showing the different shells, all built out of masonry. Of course, we're using cast iron and masonry here, and of course, we're using wood and timber frames. We probably would not be able to do this dome like we would have done, of course, in the Cathedral of Florence and, of course, Florence, Italy. But we're looking at this incredible section showing the different sections of how the dome actually meets the actual sanctuary at the center of the space. Here's another section of the entire dome, how to rest on the actual masonry of the building. Normally, the wooden timbers would be a temporary scaffolding. Of course, that's permanent. And Crusher Wren left the wooden timber frames inside the actual dome. And again, if you have an opportunity to actually climb the dome, you can actually pop out on the lantern and actually see the other towers. Of course, these incredible views of the city of London. This is a cross section showing the superimposition of St. Paul's, the smaller cathedral superimposed in, of course, St. Peter's in Rome. Here's a diagram of each one of the sections of the dome with the materials, the stone lantern, the outer of the dome, wood covered, of course, with probably lead-coated copper. Then, of course, we've seen the mixture of plaster and brick masonry. What's interesting is you can see the inner shell is really not even visible at all from the interior of the sanctuary. But what's wonderful, you can see little light patterns coming inside the interior shell onto the interior of the dome itself. So when we look at the materials of architecture and, of course, stone masonry, what's really remarkable is the fact that they lost the formula for concrete to build, of course, with the Pantheon. But for some reason, they never really had the capabilities to actually recreate the formula to actually span a larger opening. So we're reduced to sort of building these structures with brick, masonry, and stone. It's really amazing to think that for some reason, out of the years of construction and ingenuity, no one really figured out the proper ratio to build with concrete. A lot of people think that, well, how does it, there were actually some severe accidents in the stone cathedrals. A lot of people think, well, how does a stone cathedral actually burn? Well, during some of the formulation of the Gothic cathedrals, is that the wooden former would catch on fire. And of course, the limestone would pulverize and, of course, make the limestone stone, of course, the actual aggregate and material to actually make for concrete. You would think that, if they were to burn limestone, they would mix a formula to make concrete domes. But of course, they didn't have the capacity. So we're left with building what they're used to using brick, masonry, and stone and limestone. But it's really remarkable to think that, we can build these incredible superstructures with just very primitive materials of clay, tile, and brick masonry. It's really intriguing. If you look at the superstructures, is that without steel or iron, the pattern of the brickwork actually lends itself to a particular structural pattern, of course, for the actual dome construction itself. I'm going to see if I can find the YouTube video for, let me see if I can Google this one in my computer screen. And then I'll just go and change the screen. Hold on just a minute. Okay, so I think you can probably see the video here. And this is St. Paul's.
St. Paul's Cathedral features an innovative triple dome structure. On the circular drum, the inner dome rises and is visible from the cathedral interior. Above this inner dome, a brick cone rises to support the 850-ton lantern. This brick cone also supports the wood rafters and frame of the outer dome, which is covered in wood and lead. This three-dome system allows the cathedral to support such a heavy lantern, all the while maintaining the great height needed to be a visible London landmark.
Okay, let me go back to Brunelleschi's dome. There's a little video which shows the herringbone pattern. Kira, can they see the new video from the Brunelleschi's dome?
Yes, the new video is loading right now. Yep, there it is.
Okay, you can see this. Okay, good. Yeah, this professor actually built a replica of the dome.
So we're here looking at the corner of Massimo's dome. And what we can see behind the corners, we see the start of the bedding of the masonry. And as we go up, we can see the bricks in the Spinapesque pattern. And if you watch carefully, you can see that they start here and they wrap up around behind the corner and continue uninterrupted from one face of the dome to the other face of the dome.
By simply turning some bricks on their sides, Brunelleschi establishes a new pattern and achieves two important goals: preventing cracks from spreading and binding the 8 walls into one unified mass. The spiral form resists the forces of gravity more effectively than an 8-sided dome. For many, Spinapesque is the secret of the dome. But the construction of the dome involved many secrets, something the American bricklayers have come to understand from their time with Massimo Ricci. Look at that, there's a lot of these. After 2 weeks on the job, they're ready to compare their work to the real thing. The interior dome is completely covered by a religious mural. Wow. The area between the shells offers only glimpses of key elements. And plaster conceals all but a few patches of brick.
You can still see here's a good illustration. Trying to fish it. Oh, man, this is unbelievable. That's scary looking. It really is. I get to lay about anything over a little 1/5 scale. No. About the ground anymore. No. Okay.
On the way down, the workers notice something that escapes all but the most experienced eye.
See this, guys? See how this is coming up to the center, just like on the lawn? You see that? Yeah. Both of these, that's the horizontal arch right there.
The bricks are sloping down from the corner ribs toward the centers of the walls. The massive scale of the dome makes it difficult to see. But the Americans recognize its significance from Massimo Ricci. The important feature barely visible in Brunelleschi's dome becomes clear in Ricci's model. The tops of the walls don't follow a straight line as they go up. They dip from corner to corner. Within each wall, this creates an inverted arch, one of the most stable forms in architecture. These arches, combined with the spina pesce pattern, keep the bricks firmly in place, directing the weight of the masonry downward through the walls, preventing them from collapsing inward. Ricci struggled for years to figure out how Brunelleschi made it work, and how he ensured that the walls all met perfectly at the top, nearly 300 feet above the ground. Ricci was sure the answer lay in one of the primary building technologies of the time, rope lines, which Renaissance builders used to guide their work. If Ricci could figure out how Brunelleschi set up his ropes, he could unveil one of the dome's most overlooked secrets. He knew the guide ropes must have been attached to a large platform built into the base of the dome. But in what pattern?
I had to figure it out myself because Brunelleschi didn't write anything down and he didn't leave anything behind.
Niente. Ricci sketched out hundreds.
Now, there's a reason why, can you guys hear me?
Yes, we can.
Yeah, there's a reason why Brunelleschi didn't really write things down, because he didn't want anyone to copy his work. So it wasn't like he was Leonardo da Vinci where he kept an emphatic sketchbook of notes and drawings, because this is really unprecedented work. So he didn't keep notes because of that reason. He didn't want people to find out his secrets. So.
His impossible designs, trying to unlock Brunelleschi's secret. Then he heard about a 600-year-old document stored in the Florentine State Archives. It's a drawing done on parchment about 5 years after work on the dome began. It's the only surviving eyewitness sketch of the dome's construction, and it's a scathing criticism of Brunelleschi's methods. The critic, named Giovanni di Prato, detailed what he considered to be Brunelleschi's mistakes. The dome, he warned, was doomed to collapse.
He's really tearing him apart. He's trying to tear apart Brunelleschi, but in effect, Giovanni da Prato wasn't able to understand much of what Brunelleschi was doing.
Giovanni di Leonardo da Prato non è riuscito a capire fino in fondo che cosa Brunelleschi stava facendo.
The Prato may not have understood Brunelleschi's system, but he was thorough in his observations. He carefully sketched the rope lines Brunelleschi was using to guide the construction. More importantly for Ricci, Di Prato also drew the work platform to which the ropes were attached. Here, Ricci noticed something unusual, a thin line curving around the platform. To Ricci, it looked like a flower, and he immediately saw it as the key to Brunelleschi's system.
When I saw the platform with the flower drawn on it, I said, well, I'm at the right place.
Ricci incorporated the flower into the work platform of his model, using it to guide each wall's construction. Rope lines are important building tools even today, and the Americans catch on quickly to Ricci's system. One worker stationed on the platform hooks a line to the flower. Another on the top of the wall handles the other end of the rope. The rope controls the angle and the height of the bricks.
Can you see now? Hey, can you hold it there for a second? Concentrate on this one right here, this little ring. The one that Bob has a hold of, it sets the line up for that 6 feet of face. So it's essentially that guy.
And that's why the shape of the flower is so important. As the platform worker moves the line along the flower, the rope transfers the curve of the flower to the wall. This creates the inverted arch. The walls may be strong, but for the dome to work, they must meet together at the top. One small miscalculation repeated hundreds of thousands of times would lead to disaster.
With the angle, then as you go up, you should follow that all the way up. But say this was not correct. As you get that dome closing up to the top, it's not going to want to hit the middle. So you might, the dome might be this way, and might be this way.
How could Brunelleschi know his dome was on the right track? The answer is in the lines. Crisscrossing from wall to wall, they establish the center point. And before any rope line guides a brick into place, brick by brick, the walls of Brunelleschi's dome rise until they meet at the top, nearly 300 feet in the sky, and the dome is complete. For Ricci, the ropes guiding the bricks provide the real key to the mystery of the dome.
I can say with the utmost certainty, this is the true secret of Santa Maria del Fiore.
È il vero segreto di Santa Maria del Fiore.
After 2 weeks of working on Ricci's dome, the Americans seemed convinced by his experiment.
This must be the way they found it. Without putting a support underneath there, this would be the only way that it makes sense.
This flower, and it's the herringbone pattern. Those are the two things that solve the puzzle. You wouldn't be able to build a dome like that without those control measures.
Massimo Ricci has now been working on his dome longer than it took Brunelleschi to build the original. His model will remain an open laboratory for those studying Brunelleschi's method, and as an argument for the importance of the flower. It's possible that Ricci, unlike his hero, will never see his work finished.
If you look at the dates of the building, 1420 to 1436, 16 years. That's the blink of an eye. That is very, very quick. And it's wonderful to think that he saw it completed he was able to look at. He was able to walk past the building and think to himself, I built that, I did that.
With the dome, Florence moves into an entirely different dimension. The dome becomes the hub of a new city, of a new world. It's the expression of a self-confidence that no longer knows limits. People need works that can speak to them of their own capacity to dream. Brunelleschi's Dome is perhaps the biggest of those works in the history of world art.
Well, I hope everyone's still paying attention. I thought that was just a fascinating video on the nature of how to actually build something just with primitive brick and clay tiles, and look what you can do with the direction of the pattern, with the structural capacities, of course, without using concrete or steel. Well, we have about 15 more minutes. Does anyone have any questions or comments or? And can you guys see the PowerPoint again?
Yes.
Okay, yeah.
I still have a question, Jay, about I talked to you on email.
Right.
I still had not got the all the PDFs of all the slideshows for all the classes that I've attended, and I've attended most of them, but
Okay, yeah, I can send those to you later this afternoon.
okay,
I just
awesome.
have to get them organized, and yeah, but you'll get them this afternoon. Yeah.
Okay, is there some kind of quiz that we have to take for all these classes or anything?
Well, for continuing education credits, you take like a 10-question questionnaire, and it's about each one of the lectures for the whole month. And I'm not sure when that's due, but I'll get with Valerie and we can see, because to get your credits, you have to answer those questions. But
Right.
But
And
yeah,
I mean, somehow I guess I'm not on the email list. I don't know how I didn't get on the email list, but
okay, we can put you on that. That's pretty easy.
yeah. Okay, yeah, because I want to be able to take those quizzes so I can try to get the credits.
Yeah, of course. Okay.
Yeah, this was great.
Yeah.
Thank you.
Oh, no, you're welcome. And Kira, do you have any questions or comments or?
No questions or comments in the chat box.
Okay. There's one question in the chat room. Oh, yes,
Just a
geometry.
comment action. Yes, that geometry is key.
Yes. Okay, well, Kira, I think this is the last section of the class. I think the classes will pick up later in January, and I've enjoyed being the teacher. I'm sure you've seen some incredible monuments and works of architecture. So I guess I will probably see everyone in January then.
Sounds great. Thank you so very much, and talk to you soon.
Okay, thanks again, Kira.
Bye-bye.